So I decided I'd like to try to explain some of the philosophical underpinnings of physics, and my original goal and still ultimate goal is to try to explain some of the interpretations of quantum mechanics, but in a proper context, where it's not getting super into the weeds of how it works, but also without being completely wishy-washy with Deepak Chopra. But I realized to actually explain that, I kind of need to explain physics in general and how math plays into the natural sciences, particularly physics. And I also need to explain what we call classical mechanics, which classical means a lot of different things, right? It typically means that, it's a historical period, it's a musical period, although they're very separated. The classical history actually means like ancient Greece and Rome, and um, classical music, of course, takes place actually in what we would call modern history, the 18th, 17th, 18th, 19th centuries. But to a physicist, classical means not quantum, right? So there's two major paradigm shifts, right, that happened at the beginning of the 20th century: quantum mechanics and relativity. But to a physicist, quantum mechanics is the much, much bigger change in the way we think. Although maybe I'll explain relativity too on the way. So, but to a physicist, classical mechanics means pre-quantum Newtonian deterministic physics, where there's no random chance at all. And so I'm going to try to explain that, and I'm going to try to explain why quantum mechanics is such a big shift from that. But to begin with, I want to just explain one of the basic underpinnings of physics, which is two different types of numbers that exist. And so this is some mathematical underpinnings. And so, it'll be helpful to have some basic algebra to follow along here and some very basic understanding of numbers, but I'm not going to get into anything super complicated. So, without further ado, let me pull up my slide deck here of that drawn in permanent marker. So, okay, in physics, we want to label things like distance, right? So, the rest of the natural sciences, we like to describe things in terms of sort of more qualitative labels, and other disciplines of science use math and use quantitative studies, use numbers for things a lot, actually. Right? Chemists talk about the temperature of their solution, and they talk about the concentration, both of which are quantitative measures. But really, they use a lot of physics to do those things. Um, you know, pompous superiority moment. I look up tremendously to the other natural sciences. I don't think that we're better than chemists or biologists. Um, but I do love physics, and I do think it's really fun. So, but in physics in particular, we want to label quantities with numbers, right? And so we want to label something like distance, right? That's the simplest physical quantity that you might want to talk about, right? The next simplest would be time, and then the next simplest after that would be mass, or we might more commonly call weight, although there's a subtle distinction. In fact, mass, time, and length are adequate to describe any physical theory. Those are the only units you actually need, and everything else is either dimensionless, unitless, or is constructed out of those three units, right? So, but that's the simplest thing we might want to talk about, right? So, say you have some distance from your house to where you work. See those excellent drawings of a house and a work building. Um, right? So x is some number, right? So, might say, yeah, work is 3 miles from here. Okay, but is it 3 miles exactly, or is it 3.5 miles? Or is it 3.2 miles, which would just be 3 and a fifth? Or is it, 3.8294351163 miles, right? And it's like, how specific do you get? How much detail do you want to include? Right? So, we want to describe a distance, something like a distance with a number, right? Which is something we're all very familiar with doing. That door is maybe 10 feet away, right? My work is maybe 5 miles away. But, those are just, I'm just giving you the, like, uh, simplest piece of information, right? The first digit of a number that could have an infinite number of digits, right? And so, with something like that, it's up to the level of precision, right? It's like at a certain point you don't need to be more specific because it's like, you can't really perceive distances less than maybe like, 1 millimeter anyways, right? But if you want to be formal, right, most people probably see something like this, a number line, right, where we just represent, all of the numbers from positive infinity to negative infinity. Right, that's what the arrow at the end means. It goes on forever, right? So we have positive numbers and negative numbers. So what would it mean to be, negative 3 miles away from work, right? Well, okay, say work is that way, which it happens to be, right? Well, what if I pointed this way instead, right? I said this direction, which is the opposite of the way I want to go, is negative 3 miles, right? So that kind of makes sense, right? It's like, like I said, two opposites cancel, right? Negative numbers multiplied equal a positive number, right? So if I say 1 is 3 miles to the west, or sorry, actually that's the south. It's 3 miles to the south, but equivalently it's negative 3 miles to the north, right? Those are the same thing. And so typically we talk, the thing we think of are the integers, or we might say the natural numbers, it's only the positive integers except for 0. Right? So the integers are things that we can understand and count, right? I can count 1 mile, 2 miles, 3 miles, 4 miles, right? So you might say, okay, well, what if I want to be more specific? It's not actually 3 miles. It's like, maybe 3.2 miles or something. Or, I guess that would be 3 1/5 miles. Or let's say it's, 3 and, 3 3/8 of a mile, right? And it's like, well, you can just keep getting more and more specific like that until you get something that actually is accurate. Right? And so it's like, it seems like that's actually good enough, right? And if you're familiar with some mathematics, you might realize what I have, right? So up here I have the integers, right? Numbers like 1, 2, 3, 4, 5, 6, or, -1, -2, etc., including 0. Although what we call the natural numbers does not include 0, if you want to be philosophically formal. And maybe I'll get into that in the future if anybody happens to be interested in explanations of the difference between integers, naturals, reals, and rationals. But here I'm just going to talk about countable and uncountable infinities. Right? So infinity is what we call a countable infinity. Right? I can count 1, 2, 3, 4, 5, 6, 7, and I would never get to infinity, but I know how to get there. Right? And it's actually the same with what we call the rational numbers, or what we might call fractions. Right? And so if you know a little bit of math, you might recognize this grid I have written here, right? Where it's, you say like, but, fractions, I can do anything, right? I can do 1, 1/2, 1/3, or I can do 238 over 547, right? And I can just keep getting more and more specific with the number on top and the number on bottom, the numerator and denominator, until I have exactly what I want. And it's like, well, but you might also know there's numbers like the square root of 2, or pi, or Euler's number e, that have, no fractional representation. You cannot write down two numbers such that, one number divided by the other number as a fraction is equal to pi. It's impossible. And so, you can actually write out, though, something like fractions, right? You just say 1, a half, a third, a fourth, and then you say 2 halves, you say a 2 over 1, and then you have 2 halves, 2 thirds, 2 fourths, right? And some of these are redundant, but you get the idea, right? With just, all you have to do is make this grid, right? Where you have like, you keep going this way, and if you zigzag, some of you may know the trick, right? If you zigzag through this diagonally, you can very easily list with an infinite number of steps, but nonetheless you have steps, right? You know how to count to the next integer, right? So if I like go through diagonal, I go 1, I go, well, actually this has one more time. Oh, sorry. If you go 1, a half, 2 half, 1, 1, a half, 2 halves. There we go. Yeah. Two ones, 2 halves, and then 1/3, 2 thirds, and then so on. 3 over 1, etc., etc., etc. You can list all of the fractions if you take an infinite number of steps. But the key is you can take steps to do it, right? But then you take something like what we call the real numbers, right? And so with the real numbers, you just keep zooming in, right? So here's a bunch of tick marks. Say each one of these represents, I don't think I did a good job of making it. I should have made it exactly 10 or something. But, say there's, 10 tick marks here. And then you zoom in on space between just like 2 of them. And then there's 10 more tick marks. and you zoom in the space between two of those, and it's not exactly 10. I think this is probably more like 20 here. But you keep zooming in, and there's just as many numbers as you want, right? 4.99, 5, 4.9, 4.999, 4.9999, 4.999999, and you keep going with as many nines as you want, and you never run out of numbers, right? And so it might seem like that is some philosophical nonsense, and it mostly is. And in fact, it leads to a famous philosophical paradox, which is one of those paradoxes where it's like, oh my God, stop playing 3D chess with your own brain. This is stupid. But there's something called Zeno's Paradox, where you see my excellent diagram of a fast runner, or in the Zeno's original version, it was the legend Achilles racing against a turtle, right? And so the idea is that they start out with one distance of head start. Let's say a distance is 10 feet, right? So, let's even just say it's 1 foot, right? And so the paradox says, well, okay, surely this guy is way faster than this turtle. It will take no time at all for him to just catch up. Well, but before he catches up, he has to catch halfway up. Okay, you say, okay, whatever, he goes halfway, and then he keeps going, and then, in that much more time, he'll catch up. But then you get another version, where it's like, well, really, that's just resetting back to this, but now there's some distance that's half as much, so then he has to go half as much again. So he's a quarter as much, and you say, okay, this is stupid. He's just going to catch up. You're just dividing it into further, smaller and smaller pieces. And in fact, you may notice I'm dividing it into smaller and smaller pieces as rational numbers, not even as a true continuum of the real numbers, including irrational numbers like the square root of 2 and pi and stuff. But so if you're like me, this paradox is keeping you up awake at night when you start thinking about the nature of time. And it's like in a video, right, there's a cutoff, right, for how many frames per second are being recorded. But in reality, right, it's like, when does one moment end and the next begin, right? Before you get to, 1 second from now, you have to get half a second from now. Before you get to a half a second from now, you have to get to a quarter of a second from now, and so on, and so on and so forth. And it's like, well, when does it ever end? And the answer is it doesn't, as far as we can tell. There's something called the Planck time, which maybe I'll get into if I really get into enough of these. But it's a little bit strange, isn't it, right? It's like, when is there enough specificity when measuring something like a distance or an amount of time, or a speed, right? How much time it takes to go a particular distance, or how much distance you cover in a particular time, I guess, actually is how units of velocity are written. It's a little bit strange, right? And so, I don't know, I have spent a lot of time philosophizing and thinking. I've now gotten a good formal education in physics, and I've never really gotten a good resolution to this question, right? How come it doesn't take him, right? How does he ever catch up to the tortoise, right? And, those who know some calculus or know some infinite series know, right, okay, this is stupid, right? Okay, so you have to go 1, right? So you say, okay, he has to go a half, or then a quarter, then an eighth, then a 16th, et cetera, et cetera. You're like, okay, that's stupid. I know how to do an infinite series sum, right? Sum of 1 over 2 to the n, n equals 0 to infinity is equal to 1, no problem, right? But that's what one of the things that, Newton and Leibniz and his contemporaries originally realized. Is that how do you deal with situations like this where you have to have infinitely small pieces that you have infinitely many of, right? And so the difference between these two different types of infinities, countable and uncountable, turns out to be something of a philosophical nightmare. In practical terms, Isaac Newton figured out how to deal with it with calculus and infinitesimals. But it's a very interesting problem to me, and I think it's worth spending some time thinking about, right? Because if it were just fractions, there wouldn't be a problem on some level, right? There is actually a way to deal with this paradox in terms of fractions, right? You say, right, but I know how to count the steps, right? You do a half, a quarter, an eighth. And then, yeah, there's an infinite number of them, but they get smaller and smaller, and you end up with a finite sum. I think it's really strange is that, you can't necessarily do it that way, right? If you really want to zoom in all the way, there's an infinite, I guess it's infinitely infinite, right? And in fact, there's something called the Continuum Hypothesis, which basically says that uh, numbers like this, where you have a continuum, and it can just be anything, um, paper, not the explanation. And then there's things like this, where you can count 1, 2, 3, 4, 5, 6, 7, and there's nothing in between, right? And it turns out there's no way to prove that that's true. There's also no way to prove it's untrue. But there's a proof showing you can't prove that it's true, right? And it's really strange. And it bothers me a lot, actually, on some level, mostly because of thinking about time. Don't think about time, it's bad for your brain. And so, I don't know. It's like, on some level, the explanation is that numbers are a lie, right? You count, like, say you count coffee cups. One coffee cup, two coffee cup, physics. And, you know, okay, you say I have two coffee cups, but are these exactly the same? No. They're, the same size, the same shape, but they're in this case, they're manifestly different, right? They have different, like, designs and artwork on them. And so, how do you really say that you have two coffee cups, right? Well, it's really I have one jellyfish coffee cup and one physics department coffee cup, you know? And so all of math is on some level a lie, and the answer is, don't worry about it. But as a huge nerd and somebody who thinks too much, I am still interested in it because math is very effective at describing physical reality. And I spent a lot of time studying physics, and I know that it works astonishingly well. Um, a lot of things work astonishingly unwell, especially if, like me, you're an experimentalist and have actually seen the headaches of, measuring the real world instead of just like analyzing some computer data set or which some experimentalists do. Don't get me started on modern particle physics. Um, I'm a condensed matter physicist, you see. And theorists who don't, but still, I do see the effects of math working in a real way to describe the world, and that's why it's so puzzling to me, right? That on some level, the math the math like this, right, where you don't have any counting, right? You just have this method for describing quantities, and the thing that's a lie is actually numbers like this, because you say you have two of something. Well, do you ever really have two of the same thing? Well, that's why we're going to get into it, because it turns out in quantum mechanics the answer can sometimes be yes, because particles are indistinguishable, unlike coffee cups. And I'd like to get into some of that, and hopefully I'll be able to explain it reasonably well. Um, I got off to a great start here. You can see my beautiful recording studio here, aka the room where I keep my little, like, I guess, workbench for airplanes, and my desk for the occasions when I work from home. But yeah, it's something that I'd like to explore, mostly for my own edification. So I can think about things a little bit more clearly. Um, Maybe people will take some interest in it. Um, yeah, I guess next time I'll get into classical mechanics and why Newton invented calculus. And maybe if I get the chance, I can start to truly explain quantum mechanics. Because as a parting note, the thing that gets strange, right? Because I just said, right, kind of quantum mechanics is what makes this really interesting, right? Because in quantum mechanics, it's called quantum, as in quantized, as in you have things like this, where you have countable quantities, instead of just things like this, where you just get as specific as you want to about measuring something like a distance or an amount of time. And it's weird and interesting and beautiful, and nature has this wonderful way of simultaneously giving us a way to understand it, but also defying our wildest expectations. And yeah, physics is cool.